I thought when I wrote this notes thing that this would be our first conversation about this. And the great news is that sort of inadvertently, this other assignment sort of came in and wormed its way in, which was a nice unintentional sort of segue. So a lot of what we go over today is not going to be like brand new to you. There'll be a couple of new things. And then I do have an assignment that's related to this that I'll get to you once we're done. I thought this is a good time to just make a notes packet for you, and uh, why not, right? So you guys have been working with the equation that Delta Math just gives you. Like you get an equation and you work with it. What we're going to work on today is writing our own equations. So to start this out, I'm just going to give you the two equations. I'm not going to ask you to like derive it with me or some weird thing like that. So there are two versions of this vertical motion model. All we're going to talk about is vertical motion. Uh, if you're not done with the Delta Math, then when you go back to finish that, you'll still see the problems about profits and widgets and stuff. But our focus today is just things being dropped off of buildings or rocks being thrown up in the air, stuff like that, things that will fall at a predictably gravitational rate. So the first equation, write everything down now. I'm going to fill this out with you. So the first equation that we're going to use is when your problem is being expressed in feet. Because we do have to consider both sides of this, that remember, there's a whole vast majority of the Earth that uses meters instead of feet and kilometers instead of miles. So we have to consider this model from both perspectives. So when we do it in feet, we're going to have h equals negative 16 t squared plus v t plus s. And that, I mean, that's a pretty commonly accepted equation. There's a lot of variables in there. I'm guessing you already know what H and T stand for. We'll talk about the others when we get to the second section. But for now, I just wanted to get them on your notes packet so you can refer back to this time and time again. The second equation is when you're working in meters. Obviously, things have to change. Um, if you measure Earth's gravitational pull, things accelerate towards the Earth at 32 feet per second, right? But things accelerate towards the Earth at 9.8 meters per second. So you have to consider that there are different ways to express things. Like it's the same math, like the Earth doesn't care. Gravity doesn't care, just the numbers that we use to represent them have to change. So the model that we use when we're doing meters is still h, but it's going to be negative 4.9 t squared, and it's still plus vt plus s. Pretty easy to remember. I mean, the only thing that changes is the gravitational constant. So feet are negative 16, meters are negative 4.9. And those numbers are spot on half of Earth's actual gravitational pull. So um, let's talk about the variables. So I have a second section here where and you could use like a page like this on a quiz. You wouldn't have to like copy this over. I wouldn't mind if I make you a notes packet, you can use it. I don't care. So we know what H stands for, but let's write it. So H is what? The height. And the height that we get when we talk about H is, it's going to be the result of doing math at a given time. So like if I know that the time is something was thrown 4 seconds ago, then I would put 4 in place of all the t's, and that would give me h, and that would, of course, you know this from the other assignment, that would give you the height of the object at any given time. Okay. The next one that we encounter is t, and I'm guessing you know what t is. What's that? Yes. And I don't think I can say 100%, but I'm going to say it's close to 100%. Like in all my scouring of the internet to find example problems and things I could talk to you about, and all my experience, I've never seen time expressed in anything other than seconds. So, um, it doesn't seem like with the normal math that we would do to say like how high is the object after 4 minutes? Because like, you can throw a rock straight up in the air as hard as you want, and after 4 minutes, I assure you that the rock hit the ground 3 minutes and 52 seconds ago, right? So like it's not an appropriate thing to talk about minutes or hours or something like that. So this model deals directly in seconds. The next new variable is v, and it's in both equations, so it's not like you have to memorize this twice. It is. And I want to be real specific before you write down velocity. It is the upward velocity. And there's some physics involved in this that's I probably have to rely more on like Mr. Allen for a better expression or a better explanation of this. But understand that like if Steven goes out and stands on the field and throws a football and it goes up, like he's not going to throw it straight up in the air, right? If he does, then the velocity of the football is the football's vertical velocity. But if Steven throws the ball at like a 35-degree angle, he might throw that ball at 35 feet per second. But that doesn't mean that it's going upwards at 35 feet per second. So when we talk about the V, it's not the velocity of the object, it's the vertical velocity. Does that make sense what I'm saying? If you throw at an angle, some of the velocity is spent on the horizontal projection. It's not all vertical velocity. So just the vertical portion of the velocity is the v. But that'll always be given to you, like every problem you'll ever see, until you get to some more physicsy kind of stuff with like vectors and that. But when we give you problems, we're going to say like an object is thrown from a height of 4 feet with an initial vertical velocity of boom, or upward. You might see upward velocity or vertical velocity, but that's what that variable represents. Because we need these so we can build our own equations. S doesn't stand for, the letter S doesn't stand for a word that starts with S. I mean, you could make it into one, but anyone want to take a shot at what S is? It's not. It's weird. It's the initial height. And so if you think about it, like again, I'll just keep picking on Steve here. If Steve throws a football, you have to picture that Steve's release point when he throws a football is probably going to be next to his ear. And so Steve, that's probably going to be about 5 feet and 5 inches off the ground, right? So like 5.5 feet might be his S value if he throws a football. If something gets launched from a tower, you know, then the initial height might be 50 feet, depending on the height of the tower. If I hit a golf ball off the ground, what's my golf ball's initial height? 0. So understand it's like how high the object is off the ground when it begins its parabolic flight. So sometimes it's 0. If Steven stood in the bottom of a well, if he went down or like he dug a hole that was like 10 feet deep and then stood in the bottom of the hole and threw something up, then our S value would be a negative because he's starting at below ground level, below 0. So that's what all the variables represent. And you just need to know what they all are. So H is always height, V is always vertical or upward velocity, T is always time in seconds, and S is just where the object starts. Good. So the 4 questions we're going to face are in the box here. Not every question has not every math problem can be related to all 4 of these questions, as you'll see. But the main questions are, and you've had some exposure to this, how long until the object reaches its apex? How high is the apex? How long until the object reaches some specific height? And then how long until the object hits the ground? And honestly, questions 3 and 4 are pretty related to each other. Because like if I said, all right, so Shanessa is going to go out and she's going to hit a golf ball, how long does it take before it hits the ground? That's kind of the same as saying how long does it take before the golf ball hits a height of 0? So questions 3 and 4 are arguably a little bit related to each other. So to make some notes for you, I just whipped up some examples that could work together. And then I hope this doesn't take all too long. I guess we'll find out. So our first math problem is some rock is thrown upward. The angle of the throw is irrelevant because like I said, it's the vertical velocity that matters. So, I mean, if you throw the rock straight up, then it's going straight up at 52 feet per second. But if you throw it at an angle, it's traveling faster than 52 feet per second, but its vertical portion of its velocity is 52 feet. So, having said that, this applies, all four questions can be applied to this question. So, question number one, how long before the rock reaches its maximum height? What are we looking for when we talk about maximum height? Thank you, Kennedy. It's exactly right. So anytime we talk about the maximum height of an object, we're looking for the vertex. Like that is literally visually, if you looked at it from the side, the highest point is the vertex of the flight, right? So we need the vertex. And you're pretty familiar with this concept, I think. So before we can find a vertex, we need to do negative b over 2a. And then we kind of go, what the what? Like I don't have an equation. How do you expect me to do negative b over 2a? So the lion's share, I think, of today's lesson revolves around how do I write my own equations? So we're going to go back to the first page if you need to and look at our equations. And first thing we notice is that this problem is written in terms of feet. So we're going to use the top equation and we're going to write our own dang equation. Got it? So here goes. We're going to write h equals. And this part is not, this part gives no, you know what's about what's in the problem. It is what it is. So we're going to write negative 16t squared. Remember, Earth doesn't care. Our particular rock floating in space sucks things towards it at a predictable rate. The next part will change. What's the next portion of my equation going to say? 52t. Very good. So we're going to stick v, which is our vertical velocity, attach it to t. And look, we're just writing our own vertical motion model. You'll remember from the last page that it's vt, and v is the upward or vertical velocity. Good. And then we're going to finish our equation with what? Plus. There you go. So looking back on that assignment on Delta Math, you know, I don't want to talk about it at the time, but those numbers that you saw placed in those, were they like rockets, I think? The rocket problems, yeah. You can look back at those now, or if you go back and finish that assignment, you can. So again, looking back, you would see those numbers and now understand what they mean. So there, boom, we did it. We have our own equation. So let's find the vertex of the equation we just wrote. What's our negative b over 2a going to look like? Negative 52 over negative 32. Good. So at this point, you would, of course, grab your electronic calculating device and you would type in 52 divided by 32, and you would get 1.625. So that means that 1.625 is the x coordinate of the vertex. Now, this problem says how long before the rock reaches its apex. So what do we do now? This question says how long before the rock reaches its apex. So what do we do now? So this problem says how long before the rock reaches its apex. What do we do now? Nothing. The problem's over. It says how long before the rock reaches its apex. So we just take this and say, remember, you're my time, right? And it's not technically an x coordinate anymore. This stuff like this used to drive me nuts as a kid, but it's no longer XY coordinates, it's TH coordinates. So T is the time, just like it used to be our X, and H is the height, like it used to be our Y. We're done. So in this problem, I could answer it and say, okay, how long does it take before it reaches its maximum height? It takes 1.625 seconds. And now I'm ready for that other answer you guys were so eagerly trying to give me. Question 2, what is the rock's maximum height? What do we do now? This is where we have to plug it back in. So remember, the height is determined by the input-output relationship. The time is just a kind of one and done thing. So I'll calculate that. What it would look like, I'll just show my work on here, would be negative 16 times 1.625 squared plus 52 times 1.625 plus 6. According to Kennedy, it is 48.25. Is that what you said? No rounding necessary? Did it come out exactly to that? I'm just asking. No, it's not that I don't trust you. It was just a question. Is that so? You did round?
No.
Oh, okay, good.
I said you don't. Yeah.
Sorry, you're very quiet. It's hard to hear. So the height is this, and if you guys don't trust Kennedy, then you can go type it in yourself. But for the sake of saving time, I'm going to put my faith that she hit her buttons correctly. And she said that it is 48.25. And we need to label our answers. This is one of those times where without labels, we're just like being weirdos. So the answer is 48.25 feet to the nearest whole foot. So we're going to call that. I wrote this packet. You think I could follow my own directions? So we would not say 48.25. We would say 48 feet. Thank you, Irene. To the nearest foot is the nearest whole number, so we don't need any decimals. The only time we would change it would be if it's at like 48.5 or higher, which this one does not. So I would always check for reasonableness. Like I would be concerned if I typed all this into my calculator and it said 312 feet. Like, yeah, find me someone that can throw a rock 312 feet in the air. Like it ain't happening. Turn a football field sideways and stand it up and then picture someone throwing a rock that high. Ain't gonna happen. So, I mean, that's a pretty reasonable result. So I like the sounds of that. Any questions there? All right, the third question is how long until it reaches a particular height? This will be a conversation point for the day. So this is going to be a quadratic formula problem. And the idea here is that 40 is the h, right? So I'm going to take the model that we wrote up here in question 1, and I'm going to change h into a number that I want. I can be any number that you want. Since we want 40, then we're going to write 40 equals negative 16 t squared plus 52 t plus 6. And now quadratic brains kick in. What do we do to solve this equation? Get that 40 out of there first. Like we know quadratics that we want them equal to 0. Like that's just step one. Whether we go down the factoring road or the quadratic formula road, getting it equal to 0 is pretty important. So we're going to write this now as negative 16 t squared plus 52 t minus 34 equals 0. Since we're about to have to do the quadratic formula, I'm not opposed to what Jordan said. It was a little early. My what? Thanks. So I'm not opposed to pulling out a GCF. You gotta, I mean, you go either way. Like since you're going to use a calculator anyways, who really cares? But if you want to, you can divide every number by 2 if you want. So let's knock it down a notch. Why not? Because they can. So we're going to rewrite this now as negative 8 t squared plus 26 t minus 17. And this time I just elected not to write t squared and t because they're going to just be my a, b, and c values anyway. So there they are. They're sitting there. And now it's time to use our quadratic formula. So I'll need your calculator assistance probably. So here we go. So we're going to say t equals quadratic formula is x equals t equals whatever you're solving for. It doesn't matter. What goes first? Negative 26, because that's negative b. Bless you. And then we're going to put plus or minus the square root of b squared. I think 26 squared is 676, but you might want to. Oh, it is? Okay. I don't know why I know that. And then I'm going to do minus 4 times blank times blank. And I'm going to put that all over 2 times a, which is negative 16. And what am I going to backfill those blanks with? -8 and -17. Let me ask you this. Inside the square root, is that going to be a plus or a minus? It is. We're used to it sometimes cycling to a plus, but in this case, it actually cycles all the way back to a negative because there's negative times the negative times the negative. So this will wind up being 676 minus 32 times 17, which is overall 132. So our inside of our square root is done. It says -26 plus or minus the square root of 132, all divided by -16. So far, so good. In the past, the conversation has been one of the answers doesn't make sense. Let's take a look at both of these answers. Why don't we get a good set of eyes on the square root of 132? I want to know what that is. So again, calculator, square root of 132. It's 11 point. I'm going to erase this since I'm recording. Then anyone who wanted to go, oh, why did you erase that? They can just hit, the back button. So I'm going to change it into what it is. So it's 11.48913. That should be enough accuracy. I decided to round it to 5 places. If you wanted to keep all 7 or 8 places, you're fine, but that should be enough. So let's consider the top and what happens if we add. So again, assuming you've got a calculator out in front of you, let's take the plus pathway on top. Let's do -26 plus 11.48913. My top now says, I'm going to write these over here in purple, -14.51087. What's going to happen if I divide that by -16? Am I going to get a positive or a negative? I am. So let's go ahead and take that right now while it's on your screen. Just hit divided by -16. And I now have my first answer, which is, I'm going to call it about 0.907. So based on our previous experience, we would assume at this point that the other answer can be thrown out with the bathwater, right? But let's see what happens. Let's do the minus situation this time. So let's do -26, just doing the top, tracing the other pathway, minus 11.48913. I get -37.48913 divided by -16. Is that going to be a positive or a negative? It's another positive, which is going to hopefully encourage a conversation about why in the world did we get 2 answers? We'll talk about that. First, let's calculate this one. So as always, with a newer calculator, you don't have to type it in every time. That number will stay on your screen, and you just hit divided by -16, and you get 2.343. So before we leave this problem and head to part D, or number 4, let's talk about this. Why are there 2 answers? But we've taken 2 separate routes before and always thrown one of the answers away because it didn't make sense. Why do both of these answers make sense?
The rock is at 42 times.
When? How does that explain that to me? There you go. So I will draw for you a very poor excuse for a picture and explain to you. So here's the ground down here. And when you throw a rock, it goes like this. And it hits. And let's say 40 feet might be this little yellow line right here, like that. You would see that that rock crosses that threshold 2 different times. And so one of our solutions was right here. That was the 0.9 or whatever. And then it comes back down through that plane of height right here. So we will often see now that there are 2 valid solutions. And again, you guys nailed it. It's because the rock hits that height on the way up, and then it hits it again on the way back down. Okay. Let's do question 4. How long until the rock hits the ground? So let's bust through this one pretty quick. We're going to do the same thing, except this time we're going to set it equal to 0. So we're going to say 0 equals -16 t squared plus 52 t plus 6. So again, if you want to take the time, just real quick, I mean, if you're the kind of person that writes down A, B, and C like you should be, you could just divide them as you write them down. No need to rebuild the equation and then rewrite the numbers. So you'll notice that all these numbers can be divided by 2. So we can use for our A value -8, for our B value 26, and for our C value we could do 3. So our quadratic formula is going to say -26 plus or minus the square root of b squared 676 minus 4 blank blank all over double A -16. And what goes in the backfills, the blanks? Nice. Is this going to be a plus or a minus? This one will be a pluser. So what I'm going to type into my calculator this time is 676 plus 32 times 3, 96. So the inside of your square root should be 772. So the answer right now, and it's kind of not so meaningful way, is -26 plus or minus the square root of 772, all divided by -16. Let's get some feelers on the square root of 772. So again, thank you, calculator. The square root of 772 comes out to 27.78488,798. So let's use some decimals. I'll go with, I'm going to use, I think I used 5 last time. So I'll do 27.78489. So using your calculator, let's take the plus pathway first. So let's all do -26 on the top, and let's add, actually, why am I even doing this? What's going to happen if you add -26 plus 27? You're going to get a positive. And what's a positive divided by a -16? We can throw that answer out. We've seen this before, and the reason for this is because if Steven's out there throwing a rock, it's only going to hit the ground one time. At the end of its journey, the negative answer would imply that he'd have to go back in time, essentially play the video in reverse and have the rock go backwards and hit the ground before he threw it. So that answer can be thrown out. But we do have to do the minus path. So let's do -26 minus 27.78489. I got -53 and a whole bunch of decimals that I don't care about. Because while that's on my screen, I'm just going to hit divided by -16. And that answer is interesting. That's what I want. So I figured out that the rock is going to hit the ground at approximately 3.362 seconds. Got it? So far, so good? Okay, let's head to the next page. We're not going to get to the last page, and I'm really sad about that because there's something really interesting, but that's okay. My goal in the next 7 minutes is to get us through this page. I don't know if I can do that or not, but let's try to get this page done, and then we'll just resume this on Monday or tomorrow. I'm okay with that. No problems. So this time an object is just dropped from a height of 125. It's maybe on a tower, side of a building, could be a ball, something like that. I don't know what it is. It's an object. So it says we already know the maximum height, 125 meters, the time it takes to get to that maximum height. So questions 1 and 2 don't apply. You agree? Like, why would I ask you what's the maximum height? You're like, duh, it's 125. Like, it's not going to go upwards. I dropped it. So questions 1 and 2, you'll notice, are not on this page, but we do have questions 3 and 4. So how long before the object reaches a height of 50? Before we can answer questions, we need an equation. So we're going to write our equation as h equals. And There you go. Good catch there, J-Bull. This time we have to use our metric version. Good job. So our equation this time is going to be height equals negative 4.9 t squared plus what? What's the initial velocity? No, 0. So you don't need a middle term. Good job, Kennedy. The middle term does not exist with drop problems because there's a moment in time. If Kylie leans her hand out over and drops, there's an infinitely small moment in time at which that thing is going 0 meters per second. So that's the initial velocity is it's not moving, but we do need an initial height, which is what? 125. So anytime you're doing a drop problem like this, your equations are going to be shorter, which is nice. And the way we solve these, you'll see, is also, I think, significantly quicker. We don't need the quadratic formula when there's no middle term. So let's get to it. How long before the object reaches a height of 50 meters? We're only going to get one answer, right? This isn't like a ball that goes up through 50 meters and then comes back down through it. It's going to be there once. So let's figure out what that is. So we're going to replace our h with 50. Again, you can put whatever you want there because you're the boss. Once you have a model, that's the beauty of modeling in mathematics is you can apply a model to any input value that you want or output value. So the way you would solve an equation like this is a lot quicker. If you want to use the quadratic formula, go ahead. I'm not going to support it. Like I'm not going to do it with you. But what we're going to do is we're going to take a shortcut method. Step 1, we're going to move the 125 to the other side. So we're going to be left with negative 4.9 t squared equals negative 75. Everybody okay? And then we're going to divide both sides by negative 4.9. And because this is just going to be a problem where I can actually just thank my calculator for taking a square root. So I'm going to type into my calculator. Let me show my work here. Negative 4.9. I'm dividing on both sides. So I'm going to divide those out, and I'm going to wind up with t squared equals, and I'm going to type 75 divided by 4.9, and I got 15.306.12245. Now, you don't have to, again, any calculator built after like 1993, you can leave that number on your screen. Bless you. And most of your TI calculators, if you're using a Casio, you'll have to come see me and I'll help you problem solve this. But on any calculator that's a Texas Instruments, if you hit, don't do this yet, but if you hit the second button and then the negative, do you see how right above the negative it says ANS? What that does is it pulls up a previous answer. So I'm going to hit the square root button first. I'm going to hit second square root. And then I'm going to hit second negative. And what my calculator says is it has a square root sign, a parenthesis, and then it says ANS. And that's just the calculator's way of saying, oh, so you want me to take the square root of the number you just got? My answer is yes, please. So I hit enter and I'm done. And I figure out that the answer is 3.912. And that'll be good enough for me. Technically, it would be a positive negative. Like I have to say this, so the math gods don't strike me down today. When you take the square root of a number, it really should be positive and negative. But why would I even consider the negative? Like, what are you doing here? So I'm just going to take the positive that my calculator gives me, and I'm going to call it 3.912 seconds. Okay. So that one was pretty easy, huh? So it's nice. The drop problems are nice because you can solve them a lot quicker. And then how long until the object hits the ground? Let's see if we can motor through this real quick. If you just give me 2 minutes without packing, I'd be infinitely grateful. Let's take 0 and put it in place of like where the 50 was. So we're going to say 0 equals negative 4.9 t squared plus 125. So what are we going to do for this one? Move the 125, right? So we're going to wind up with negative 4.9 t squared equals negative 125. And then from here, bless you, the calculator does all the lifting. I'm going to divide 125 by 4.9. And I'm going to get a number. And quite frankly, what that number is, I don't care. I don't even kind of want to write it down in the notes. It's just some number. It's what t squared equals. And so what am I going to do now with my calculator? It's okay. Thank you. We're going to square root it. The number that's staring at me is 25 point numbers. I don't care. So while it's on my screen, I'm going to hit square root of previous answer. And that's the number that I care about. And I got 5.051. I rounded a little bit, but the time in this case is approximately 5.051 seconds. I really wish I could have gotten to the last problem, but the clock, at the end of the day, I cannot defeat the clock. So I'll pause it. I won't pause it. I'll stop this here. Tomorrow we'll do the last one and I'll give you your assignment 50. Got it? All right.